Hello everyone, I'm Srinivas Varidhasan. Okay, I have a mini project of a simulation called Digital Thermometer with OLED Display, supervised by Associate Professor TS Technologies, Dr. Mohammad Izanuddin bin Abdulaziz. Okay, today my presentation will cover the abstract, introduction, literature review, problem statement, proposed solution, methodology, um, result and discussion, applications, impact and commercialization, conclusion and future work, and references as well. The abstract. The goal of this project is to use a microcontroller and Python programming to design and create a digital thermometer with an OLED display. It uses a sensor to monitor temperature in real time, which is then shown on a 128 times 64 OLED screen. MicroPython or Circuit Python is used to program the system, which is constructed with an ESP32 or Raspberry Pi Pico and a TS18B20 or DHT22 sensor. The SSD1306 driver uses the I2C interface to read temperature data, convert it to Celsius, and display it. A computer's Python software can use wireless or serial connectivity to capture and examine the readings. This project, which emphasizes affordability, ease of use, and education, illustrates the principle of microcontroller and the Internet of Things, which is IoT. Possible improvements includes cloud monitoring and humidity sensors. Next is the introductions. On the background, in contemporary applications such as manufacturing, robotics, and healthcare, temperature monitoring is essential. Temperature data can be measured, displayed, and analyzed in real time for both practical and instructional reason using inexpensive microcontroller sensors such as DS18B20 and OLED screen with Python programming. Under motivation, through the integration of hardware and software, this project offers practical experience in sensor interfacing, I2C communication, display control, and Python programming. It's affordable, instructive, and perfect for prototyping, allowing for data logging, real-time temperature display, and potential extension with more sensor or connectivity. Next is the objective. This project's primary goal is to use a microcontroller and Python to create a digital thermometer with an OLED display. It seeks to measure temperature accurately using a ESP32 or Raspberry Pi Pico and a DS18B20 or THT22 sensor. Next, B. Use MicroPython or Circuit Python to display readings in real time on a 128 times 64 OLED, which is SSD 1306. The third one, okay, C. Send data wirelessly or via USB to a computer for logging and graphically analyze using Python. Next is the literature review. So the integration of Python based microcontrollers such as ESP32 and Raspberry Pi Pico for real-time temperature monitoring and DSP18B20 or DHT22 sensors and SSD1306 OLED screen is highlighted in this literature review. Effective data interchange is made possible by communication protocol like I2C, one wire, and UART, while data logging and visualization are supported by Python utilities like PySerial and Matplotlib. Reliable implementation techniques are validated by community tutorials and datasheets. MicroPython simplifies embedded development while preserving accuracy, responsiveness, and expandability in temperature measurement and monitoring system, as evidenced by the evaluate research emphasize on educational value, low cost prototype, and scalability towards IoT applications. Next, the problem statement. Conventional thermometers lack data logging and connectivity, despite the fact that temperature monitoring is crucial for process management, safety, and comfort. For education, commercial option, which sophisticated features are frequently expensive and rigid. Using a Python program microcontroller, MicroPython, to read temperature from a digital sensor and display it on a OLED screen. This project create a low-cost programmable digital thermometers. Additionally, data is sent to a computer for visualization and logging. The system provides an instructional, useful, and scalable platform for learning EMPT system by merging hardware and software. It also lays the groundwork for future IoT-based temperature monitoring applications. The proposed solution, a MicroPython program, microcontroller, ESP32 or Raspberry Pi Pico, a digital temperature sensor, TS18B20 or DHT22, and a 128 times 64 OLED display, SSD1306, are used in this project to create an inexpensive digital thermometer. The microcontroller uses one wire or proprietary protocols to read precise digital data, convert it to Celsius, and then use I2C to display it. Temperature readings are transmitted via UART to a computer where they are logged and shown by a Python script using Pi serial and Matplotlib. The system allows for future improvement like humidity monitoring, wireless data transfer, and IoT-based cloud integration while showcasing important end principle like sensor interfacing, display connection, and data processing. Meteorology. This is the simulation flowchart. So it will be having, it will start, then it will be going to the set simulation config. Later it will initialize the model, then it will generate the sensor value. After then it will start to validate the reading. If it's incorrect, it will be record error frame or retry or skip to wait until next tick. If the reading is valid, if it's correct, then it will format the frame, timestamp, and temperature. Then it will update the OLED mock, example like 27.4 Celsius. Then it will send via serial mock to CSV line to log to CSV or buffer and optional live plot. Okay, then if the condition didn't meet, then it will generate sensor value, base, drift, and noise back to follow. If the condition meet is correct, then the result will be saved as CSV, PNG, and stat. So the simulation will be ending. To conclude the simulation flowchart, the simulation configuration, which includes sampling data rate, duration, base temperature, noise, and drift, is first set in the flowchart. The virtual sensor, OLED mock display, serial fake logger, and a plotter are among the modules that the system then initializes. Next, it uses base, drift, and noise to generate a sensor value. If the reading is not legitimate, the software either skip it or reports an error. The reading is formatted with a timestamp if it is valid, display on the OLED mock, transmitted via serial mock, and recorded for real-time charting. The system saves results, CSV, PNG, and states, and terminates after waiting for the next cycle till the stop condition is satisfied. Okay, so this is the Python coding's implementation. So the left side is the coding and the right side is the explanation. So for this coding, I can explain that it imports the following library. So the NumPy is actually which is used for random number creation and mathematical computation. Okay, the pandas for data frame is used for data analysis and organization. Plotly express and graph objects for making interactive chart into 2 and 3 dimensional, which will be shared later in the result and discussion. Okay, for this stimulate and sensor data Python coding. Okay, the explanation is actually for the 100 time point of sensor readings are simulated for the temperature where varies using the sine function plus random noise. Humidity, cosine function mimics the oscillation of humidity. Next, for ambient light, the slower oscillation that show variation in light intensity. Next, for voltage, little sinusoidal oscillation that mimics variation in sensor power. Next, repeatable outcomes are guaranteed by NP random seed, which is 42. Okay, to conclude this, it creates a Panda data frame, a structured data set with column for time, temperature, humidity, ambient light, and voltage by combining all created array. Alright, for the next is generate 2D chart. For 2D chart, actually, the explanation is makes a 2D line chart to show how the temperature changes over time. This make it easier to spot irregularities and recurring changes. Creates a scatter plot that illustrates the connection between temperature and humidity, beneficial for analyzing correlation creates a histogram that show how ambient light intensity is distributed. Draw attention to the frequency of specific light intensities. Next, show variation in power supply or sensor voltage stability by displaying a bar chart of voltage value against the time. Next is the generate 3D charts. So the explanation is actually produce a 3D surface plot that illustrates how temperature varies with humidity and time, helpful in comprehending integrate integrations, provide a comprehensive perspective of environmental data by creating a 3D scatter plot that plots temperature, humidity, and ambient light together. Temperature intensity is represented by colors. Okay, explain that genuine 3D bar charts are not supported by Plotly by default, so it recommends alternative 3D bars visualization such as Mesh 3D or Matplotlib. For the fabrication and measurement setup under this methodology, initially the prototype was put together on a breadboard using a DS18B20 temperature sensor that was connected to the microcontroller via a 4.7 kilo ohm pull-up resistor and a 3.3 volt supply. I2C was used to connect an SSD 1306 OLED display, which is 120 x 64 SDA SL. Following successful testing, parts were encapsulated for stability and mobility and put on a prototyping PCB. The system was powered by a 3.3 watt supply or USB, and it was given time to stabilize before being measured. Every second, temperature reading were recorded and shown on the OLED in real time. Following a DS18B20 OLED wiring tutorial, data were concurrently sent to a computer for logging and analysis before being calibrated against a reference temperature under controlled conditions. Next, result and discussion, temperature over time, line chart. Okay, so this gives us that the accurate simulation, dependable data collecting, and efficient Python visualization for real-time temperature monitoring are confirmed by the sinusoidal graph, which display temperature cycling between 15 Celsius and 25 Celsius with slight noise. Next, for temperature versus humidity scatter plot. Okay, the temperature and humidity have an inverse relationship as demonstrated by the scatter plot's oval pattern, which validates precise sensor response, dependable data gathering, and efficient Python-based visualization for examining genuine environmental behavior. Next is the ambient light distribution histogram. Okay, this histogram shows that the reliable sensor performance and accurate simulation of ambient light behavior are confirmed by the histogram, which primarily displays light intensity between 300 and 350 units, indicating steady condition with few outliners and slight changes. Next, for voltage fluctuations over time bar chart. Okay, the bar chart shows that the voltage oscillation between 3.2 and 3.4 are displayed in the bar chart, signifying a steady power supply. Okay, low noise and dependable electrical power performance appropriate for continuous real-time sensor monitoring applications. Next, for the 3D surface plot, okay, the temperature versus time and humidity. Surface plot is showing the realistic atmospheric behavior, dependable data production, and efficient Python-based visualization for multi-dimensional environmental monitoring are all demonstrated by the 3D surface plot, which display an inverse relationship between temperature and humidity over the time. Next, the 3D scatter plot for temperature, humidity, and ambient light. Okay, realistic environmental patterns, reliable sensor simulation, and efficient Python-based visualization for multi-dimensional monitoring in Internet of Things and smart environment applicable are all revealed by the 3D scatter plot, which displays correlations between temperature, humidity, and light. All right. For the applications, okay, there are numerous use for the digital thermometer system in various industries. It allows for energy efficient temperature control and monitoring in smart home using Python logging and a OLED display. It can also be used for equipment protection and process safety in industrial setting, greenhouses, and stations. In food logistics, it prevents cold chain integrity with real-time notifications, while in the healthcare, it guarantees appropriate storage and environmental conditions. It also facilitates prototyping, educational, and do-it-yourself applications, teaching students about data visualization and M system. All things considered, its price, flexibility, and data integration make it useful for real-world automation projects and Internet of Things-based monitorings. The impact and commercialization. There is a lot of commercial and educational possibilities for this initiative. Using inexpensive parts like ESP32, DS18B20, and OLED display, it gives students practical experience with Python programming, sensor interface, and IoT system design. It's inexpensive, modular design facilitates commercialization and scalability through industrial data loggers, smart home appliance, and instructional kits. Cloud-based monitoring may be possible with upgraded models that have Bluetooth or Wi-Fi. The design's scalability and simplicity complements the expanding Internet of Things IoT industry, which is expected to reach USD 1.4 billion by 2030. This make it appropriate for industrial, residential, and academic applications and encourage innovation in smart environmental monitoring system. Conclusion and future work. Using an ESP32 or Raspberry Pi Pico, DS18B20 or DHT22 sensor and a SSD 1306, OLED display for real-time management and Python data visualization, the project effectively creates a MicroPython based digital thermometer. It provided practical experience with MD system, sensor interface, and Internet of Things concept while demonstrating affordability, accuracy, and instructional value. Future upgrades will incorporate several sensors for environmental mapping, add wireless connectivity like Wi-Fi, Bluetooth, LoRa, for cloud monitoring, and improve analytic with Python-based prediction and warnings. The system can develop into a scalable Internet of Things solution for household, industrial, and agricultural automation applications, which its sturdy shell and intelligent automation features. These are references I use for my mini projects like from Edge Microtech, Research and Markets, Instructables, Indoor Environments, Random Nerd Tutorials, SwitchDoc Labs blog, then Deep Sea Development. Thank you for watching my presentation. Okay, again I repeat, my name is Srinivas. Thank you.